As we've seen, a current-carrying wire will set up a magnetic field around it. And if we bring in another magnetic field near that wire, then a force is going to be exerted on that wire. What we're going to look at now is a condition where we have two parallel current-carrying wires, both of which set up magnetic fields around them, and both of which will experience forces. And we're also going to look at the forces, the magnetic forces, on a current-carrying loop of wire. So, let's get started. Alright, so we know if we have a wire and we run a current through it, it sets up a magnetic field around it. So if we run another current-carrying wire near that first wire, it's going to set up a magnetic field around it as well. Both of these wires then are going to experience magnetic force between them. Due to Newton's third law, though, we know that the force experienced by one wire will also be experienced by the other wire. There will be the same magnitude force. It's Newton's third law. The result is that these fields, depending on the direction of the field, will either attract or repel the two wires. Now, what determines the direction of the field between the two wires is the direction of the current in the wire. So we can say that the magnetic fields around current-carrying wires are either going to attract or repel each other depending on the direction of the current running through those wires. Now, in this picture, we have two wires separated by some distance r. Both wires carry a current in the same direction, and we call this wire 1 and wire 2. Now, both these wires are going to set up a magnetic field around them, but let's focus first on just the magnetic field set up by wire number 1. If we want to know the magnitude of the magnetic field set up by wire 1, we're going to use this equation here that we have been calling buoy. Now, once we've figured out the magnetic field set up by wire 1, it's as though, as far as wire 2 is concerned, there's just some magnetic field over here, okay? It could be like we've stuck a magnet next to wire 2, as far as wire 2 is concerned, okay? So, if we want to find the force on wire 2, which is going to be equal to the force on wire 1, right? We're going to use this equation here we call Bill. So really what this is saying is the magnetic force on wire 2 is equal to the magnetic field set up by wire 1 times the current in wire 2 times the length of wire 2. And it's in this way that we use Bill and buoy to figure out the magnetic force between those current-carrying wires. The first thing to do is pick one of those two wires and use buoy to figure out the magnitude of the magnetic field, then use Bill with the other wire to figure out the magnitude of the force. Now, like we say here, right, the direction of that force is going to be either attractive or repel because of the direction of the current in those two wires. Let's take a look at how that works real quick. Okay, so here we have two sets of two parallel wires. On the left-hand side over here, we've got two wires where the current is in the same direction. On the right-hand side, we've got current traveling in opposite directions. Now, if we look at the right-hand rule for each of these situations, we see that on the left-hand wire over here, when that current is traveling through it, the magnetic field that's set up will be going into the page in that space between those two wires. So in this space here between the two wires, this magnetic field set up by wire 1 is going down into the page. The magnetic field set up by wire 2, though, is coming up out of the page, okay? So what we have here is magnetic fields in opposite directions. So it's like opposite poles here, and we end up with a force that is attractive between those two wires. So when the current in the wires is running in the same direction, the magnetic field between the wires will be in opposite direction, and the force will be attractive. On the other side, where we've got the current traveling in opposite directions, we have here a field between the wires that's going into the page. And on the other side, where we've got the current traveling in the opposite direction, between the two wires, the magnetic field is going into the page as well. So here we've got the current traveling in opposite directions. The magnetic field between the wires will be in the same direction, and the force between them will be repulsive. So what we have to remember there is when the current is traveling in the same direction, they're going to attract. when the current's traveling in opposite directions, they're going to repel. In the same way that straight sections of current carrying wire will have forces exerted on it when placed in a magnetic field, a current carrying loop will also be affected by a magnetic field. So in this drawing here, we've got a loop where it is free to rotate on either end, and it's placed into a magnetic field. Each side of the loop then is in that magnetic field. The current goes up in one side and down in the other side. So there's a magnetic field exerting a force on each side of that loop. The forces are in opposite directions by right-hand rule, which causes a torque. The loop then will rotate. This is the principle behind electric motors. Over here we see the situation looking down from above that loop. As the loop rotates, the force and the direction of the field stays the same, but the direction of the velocity changes. As the loop changes position, the torque will vary between 0 and some maximum value. The maximum torque will occur as shown in the first drawing, when the loop is moving perpendicular to the lines of force. The minimum torque, zero torque, occurs when the loop is traveling parallel to the lines of magnetic force. And this can be seen in this drawing here. So the maximum torque occurs when the loop is in this drawing 1 here. This is where the motion of the loop is perpendicular to the lines of force. As the loop rotates, the torque decreases because the force is getting smaller. As that angle decreases, the torque also decreases. And when the angle is 0, the torque is 0. Now, this idea of current carrying loops being able to rotate in a magnetic field is the principle behind all electric motors. The simplest electric motor is made up of simply a loop in a magnetic field. So that's this drawing right here is a simple motor where we've got a magnet here, wire here, we got run a current through that wire loop. This wire loop would then rotate as those torques act on that loop. This motor here shows just a single loop of wire. In reality, motors have hundreds or even thousands of loops, but for simplicity's sake, we just use this example that has just one loop. The way the motor works is the current flows from the battery into one of these sides, one of these little brushes here. This gets that current into that loop, where that current flows through the loop to the other ring, where it flows back into the brush and then back into the battery. There then is a path for the electricity to flow. The loop is conducting current, so it develops a magnetic field. This field attempts to align itself with the permanent magnetic field already there. This causes a torque which makes the loop spin. It would normally rotate until the torque was 0, at which point the loop would come to rest as its magnetic field would be aligned with the permanent magnetic field. But the split rings prevent that from happening. Right here, these split rings prevent that from happening. Just as the loop reaches the point where the torque will be 0, the open part of the split ring comes under the brushes and the current stops. The loop keeps rotating because of its inertia. The other split ring rotates under the brush and electricity begins to flow again, except that the direction of the current is opposite to what it was before. This applies a torque which pushes the motor in the same direction as it was going. The loop keeps spinning. In real motors, the loop is like a coil wrapped around some sort of ferromagnetic material like soft iron. Most motors have more than one coil. Each of the coils is called a pole, and most motors have at least 3 poles. The good ones have like 5 or 7 poles. Another pretty cool application of the force exerted by a magnetic field on a conductor is your basic loudspeaker. The parts of a loudspeaker are, you've got like a paper or plastic cone right here, a magnet base, and a coil of wire. The way the thing works is a small electric signal is sent to the coil from some sort of amplifier, such as a radio or CD player or whatever. This is a signal that will vary with the music or whatever sound is being sent. That is, the current is going to increase or decrease with the music. The amount of force exerted on the coil by the magnetic field then varies with the strength of the current. When the current increases, the force increases. When the current decreases, the force decreases, and so on. So the coil sits in a slot cut into the magnet. When the force exerted on the coil then causes it to move back and forth with the music. This also vibrates the cone, which puts sound out into the air. So we've also talked about electromagnets and a little bit about what's called magnetic permeability. Magnetic permeability is a property of a material that has to do with how the material changes the density of the magnetic field passing through it. Some materials, like iron, are really permeable to the lines of flux. These lines of flux are attracted to the material and pass through it rather than through air. Material with low permeability would have little effect then on the lines of flux, the magnetic field lines. Material with high permeability would dramatically change the flux density of the magnetic field. So in a ferromagnetic material, those lines of flux would be concentrated in that highly permeable material. In a diamagnetic material, it's less concentrated. Okay, so we can see from all of this that a current carrying conductor will set up a magnetic field around it. That magnetic field can then affect other conductors with current running through it. We can use these principles to make things like electric motors and speakers and several other things. From here, we're going to go on into what's called electromagnetic induction, where we are looking at how we can create magnetic fields. We'll take a look at that next time. See you in class.